Hi, and welcome to Module 4.8 of Digital Signal Processing, in which we will talk about the short-time Fourier transform. The short-time Fourier transform, or STFT for short, is not a new kind of Fourier analysis. It is just a clever way of using the DFT to analyze the properties of signals that evolve over time. We will see why we need this tool, first by comparing the advantages and disadvantages of the time domain and the frequency domain representations for a signal. Then we will talk about the STFT and of the spectrogram, which is the graphical way of representing short-time Fourier transform data, and we will briefly talk about time-frequency tilings. Let's start with a very concrete example, and let's talk about dual-tone multi-frequency dialing, or DTMF for short. This is the way analog telephones work. Whenever you press a button here in the dial pad, you generate a sound which is composed of two sinusoids. The frequencies associated to the sinusoids are given by this matrix here. So here is the keypad of your telephone, the digits 0 to 9, plus the pound and the star signs. And when you press a button, say you press digit number 4, you generate two sinusoids, one at 770 Hz and another one at 1209 Hz. These frequencies have been chosen so that they are coprime, and also so that no sum or difference of two different frequencies correspond to one of the frequencies in the set. The idea behind this choice is to minimize the possibility of error when the telephone central office tries to decode the sequence of numbers that you have dialed on your phone. So here's, for instance, what happens if you dial 159 on your keypad. You generate a signal that sounds like this. Now, if we plot the signal in time, we get something that looks like this graph here. So we see that there are indeed three bursts of sound with a pause in between, but it's absolutely impossible to understand which digit has been pressed just by looking at the time domain plot. We know when the digit has been started and when it ends, but we don't know its value. And even if we zoom in, it's very difficult to understand which frequencies make up this shape in time. On the other hand, if we take the DFT of the signal, we can see these frequencies very clearly. If you remember the DTMF matrix, each digit has a pair of frequencies associated to it, a low frequency and a high frequency. And so these will be the frequencies associated to the digit number 1. These are the frequencies associated to number 2. And these are the one associated to number 3. But we cannot tell in which order these digits have been pressed. So the time representation completely obfuscates the frequency content. So we know the timing, but we don't know the content. The frequency representation obfuscates the time information. So we know the frequencies, but we don't know when they happen. So the idea behind the short-time Fourier transform is the following. Instead of looking at the DFT of the whole signal in one go, we take small pieces of length capital L, and we look at the DFT of each piece. So the DFT coefficients now are indexed by two variables. M is the starting point for the localized DFT, and K is the DFT index for that chunk. So this is your signal. You start here at M, you take L points, and you perform a DFT. And then you move M to another point and compute another L point DFT, and so on and so forth. The values of the STFT coefficients for M and K are given by the sum from 0 to L minus 1, so a standard DFT over capital L points of the signal samples starting at M times e to the minus j 2 pi over L and K. So let's apply this strategy to the DTMF signal. We have 16,800 samples, and we take a window size of 256 points. And suppose we start at 0, we take therefore the DFT of this little chunk. The content of the chunk is pure silence, so the DFT coefficients will be identically 0. Here in the lower plot, we show the first half of the DFT vector because the signal is real. Now we move the analysis window in the middle of the first sound burst. And now the DFT coefficient indeed shows us the two frequencies associated to digit number 1. we move the window to the second burst, and we can see that now the DFT coefficient show the frequencies associated to digit number 2. And you can compare this to the previous peaks, and you see that they have moved. Finally, when we move to the third burst of sound, we have the frequencies corresponding to digit number 3. You can notice that the amplitudes of the peaks are not uniform, in spite of the fact that the signal is of equal volume. The reason is because the position of the window influences the amount of energy that we capture for the DFT. So here, for instance, in this case, probably we're spanning a little bit of silence before the onset of the waveform, and therefore the peaks are lower than in the former cases. The spectrogram is a clever way of showing this time-varying spectral information in one single plot. If you think about it, the short-time Fourier transform is a complex-valued function of two variables, m and k. And so to plot it properly, we would need a four-dimensional plot, which of course is not possible. We can restrict ourselves to the magnitude of the DFT, at which point the SDFT becomes a real-valued function of two variables, which requires a three-dimensional plot. Now, this is not only quite hard to do, but also rather difficult to interpret. To make it easier to understand, what we do instead is color code the magnitude of the Fourier transform. And we use dark color, dark hues for small values, and whitish or brilliant hues for large values. We also take the logarithm of the magnitude in order to compress the range of values that are associated with the magnitude and to better map them over a color scale. And we put the spectral slices one after another to obtain an image-like picture of the time-varying spectrum. So this is the spectrogram of the DTMF signal. On the horizontal axis we put the variable m, so the starting point for each spectral slice. Here on the vertical axis we put the DFT coefficient. We have a real signal, so we just go from 0 to L/2, where L is the size of our DFT window. You can see here that the black pixels in the picture correspond to very small values for the DFT. So these black areas indicate the silence regions in the DTMF signal. At the same time, the bright bands here correspond to high values of the DFT coefficients. So these are actually the frequencies in each digit being dialed. And so in the plot we have shown at the same time both the time information, we have a good estimation of where each digit begins and ends, and of the frequency content that is associated to each digit. So we can read this picture and find out that the digits were 1, 5, 9 in sequence. If we know the system clock for the signal or the sampling rate, we can label the axis just in the same way we did for the DFT. So remember, the highest positive frequency is fs/2, where fs is the sampling rate of the signal. The frequency resolution, how fine a frequency we can resolve in the DFT, will be given by fs/L, and the width of the time slice, so the time resolution, is L times Ts seconds, where Ts is 1/Fs. So if we apply this to the DTMF signal, which was sampled at 8 kHz, we can label the axis like so. We have a maximum frequency of 4 kHz and a total duration of the signal of 2.1 seconds. The natural questions that should come to mind at this point are, what about the width of the analysis window? We chose 256 points. Why? Is it the optimal size? What happens if we take a larger window? What happens if we take a smaller window? How do we position these windows along the signal? Do they overlap? And if so, by how much? And what is the shape of the window that we should use? By shape here, I mean the following. Here we're taking chunks of L samples and just taking a DFT of the raw data. Now suppose my signal is a very smooth signal over this window that goes like this. So this is a smooth signal, and my DFT should have basically just low frequency coefficient. But now remember that to the DFT, everything is a periodic sequence. So what the DFT really sees is something like this. Now here we have all of a sudden a big jump at the discontinuity. And this will create spurious high frequency content in the DFT coefficients. We can counteract this side effect by taking the raw data in each chunk and using a tapering window. So for instance, suppose we have a tapering window shaped like a triangle. We multiply each sample by the value of the window, and we will have a signal that is pretty much identical to the original data in the middle of the window, but then it tapers to 0 at the extremities. And so in the end you would get something without jumps in the periodized version, like so. So the whole story is that we could really spend weeks talking about all the tricks and tweaks that we can apply to a spectrogram in order to extract some kind of information from a real-world signal. But since we don't have that kind of time here, we will just talk about the main trade-off, which is related to the size of the analysis window. Spectrograms can be either wideband or narrowband according to the frequency resolution of the associated DFT. So if we choose a long window, if our L is big, in that case we have a narrowband spectrogram. Why is that? Because a long window will give us more DFT points and therefore more frequency resolution. Remember, the frequency resolution in the end is equal to the sampling frequency divided by L, or 2 pi divided by L if we remain in the complete abstract discrete time world. However, in a long window, more things can happen, and so we have less precision in the time resolution. In the limit, a long window is the DFT of the entire signal, and we have seen that that completely obliterates the time information. Conversely, if we choose a short window, then we have a wideband spectrogram. A short window will create many time slices, because you will divide the whole support of the signal into more chunks. And so we have a much more precise location of the transitions. But a short window will give us fewer DFT points, and so the frequency resolution will be poor. So let's use our DTMF signal once again and look at the difference between a wideband and a narrowband spectrogram. Here is an example of a wideband spectrogram where the analysis window is just 32 samples. With such a short analysis window, we have a very good localization in time of the start and stop point for each burst of sound, but you can see that the frequency bands are extremely wide. Also, having a very short window creates artifacts in the high frequency range, because as we sweep the window over the signal, we will be encompassing uneven numbers of periods for the underlying sinusoids. This is a spectrogram that we saw in the beginning. The window now is 256 point. So let's say that this spectrogram is in between an extremely narrow band and an extremely wide band. This is a very good compromise to interpret what's going on in the signal. If we increase the size of the window to 1024, so 4 times larger, then we have an extremely narrow band spectrogram. You see now that the frequencies are localized extremely precisely, but on the other hand, the time resolution is very poor. We're completely missing the silence here in the beginning, for instance, and the silence between these two digits. Spectrograms are particularly useful and particularly popular in speech analysis. Speech is a particularly difficult signal to analyze because the mechanism of speech production alternates between widely different modes of operation. When you pronounce a vowel, a sound like ah, for instance, you're producing a harmonic sound that resonates in your body and that contains a very well-structured harmonic content. On the other hand, consonants have a noise-like structure mostly, and their spectral makeup is completely different. So it would be futile to try and come up with a global spectral representation for an entire speech utterance. And we need to split the speech into pieces and analyze these pieces in sequence. So here's an example. This is a sentence from a speech corpus that is used in speech analysis algorithms.
There is a lag between thought and act.
So in the time domain, the waveform can be split like this. This part here is there is a lag. This is between thought and act. So here we are in the presence of a portion of speech that is rich in vowels. And here we have single words that have both vowels and consonants. In particular, for instance, look at this. This is act. And so we have A and then C and T, which are noise-like pulses. The speech signal was sampled at 8 kHz, and let's try and see what a wideband spectrogram can tell us about the structure of this utterance. So if we take an 8 milliseconds analysis window, which gives us frequency bins of 125 Hz, which is quite wide, we get a plot like this. We cannot see much in terms of frequency resolution, although we start to see some patterns here that will be clearer later. But what we do have is very precise onsets for the consonants. Remember, this is act, and see here you see the beginning of the C, and here you see the beginning of T in this onset of a high energy band in the spectrogram. And the same could be said for the other consonants. If we use a narrowband spectrogram, so we increase the analysis window to 32 milliseconds, now we have a resolution of 31 Hz. And here we see the harmonic structure of speech. Here the focus is on the vowels, and here you can see that each vowel contains a harmonic structure that depends on the pitch of the vowel, and it will change from speaker to speaker, from male speaker to female speakers. You can also see how in speaking we modulate and change the frequency of the vowels to give a certain intonation to our utterance. So narrowband spectrogram will give us information on the harmonic parts of speech. Wideband spectrogram will give us information on the pulse-like and noise-like consonant sounds in speech. The short-time Fourier transform determines a tiling of the time-frequency plane where the size of each tile is specified by the time and the frequency resolution of the STFT. Suppose you choose a window size equal to 20. What we'll have is a subdivision of the time axis into chunks that are 20 samples long, and a subdivision of the frequency axis into bins, each one of which is 2 pi over 20. So each tile in the frequency plane will have a horizontal size of 20 and a vertical size of 2 pi over 20, and everything that happens in the time frequency plane within this tile will be summed up by just one STFT value. If we change the size of the window, suppose we take L equal to 10, then we narrow the size of the tile in the time axis, but we widen the size of the tile in the frequency axis. So although the shape of the tiles change, the number of tiles remains the same, because the area of each tile remains constant. Similarly, if we shorten the window even more, we have a different arrangement of the tiles, but the size of each tile remains the same. This is actually quite self-evident. If the time resolution is L, the frequency resolution is 2 pi over L, and therefore the product, namely the area of each tile, is the constant 2 pi. In a nutshell, this is the uncertainty principle in time-frequency analysis. It states that we cannot arbitrarily narrow our focus both in time and in frequency. If we want a higher time resolution, we will necessarily have to give up frequency resolution and vice versa. The short-time Fourier transform leads to a very simple, uniform tiling of the time-frequency plane, and more sophisticated structures have been the subject of much research, and in particular of a branch of signal processing called wavelet analysis. For those of you who are curious about wavelets, we recommend you check out the links that we provide in the bibliography for the class.